Hey everyone, in today's video we're going to have a look at enhancing materials. So what you need to be able to do is basically identify how and why you should enhance polymers, timbers and metals and what the process for doing that would be. So if you've got your textbook with you, so it is from page 39 to 44 in your textbook. So we'll start with polymers. So first of all, before we start, for the most part, polymers are what are called inert, which means that they resist chemical, insect and fungal attack naturally anyway. Some materials are more prone to things like that, so obviously timbers are more prone to insect and fungal attacks, so rotting and that type of thing. First, polymers naturally resist that anyway. However, certain characteristics of plastics can be enhanced using something called additives. Now, we've talked about additives before a little bit, but I'm going to go into more detail about the different kinds of additives that you can have. So first of all, we're going to improve the actual physical function of a polymer. You can add something called flame retardant. So we'll start at the top and work our way around. So flame retardants, that's where you can add things like bromine, chlorine, or phosphorescent material. When added to a polymer, reduces the likelihood of combustion or the spread of fire. So combustion basically is if you have a material near an extreme heat or a flame, how likely is that material to then go up in flames? So with obviously in most people's house, well, in everyone's houses, you've got electrical plugs that are probably made out of ABS or something similar. So you need to make sure that it's got good flame retardant, flame resistance, flame retardants on it, so it doesn't catch fire. You've got fillers. So your most common fillers are things like sawdust and wood flour, and they can be used to essentially bulk out the material, so you don't use as much plastic. So this will help material conduct conduct heat a little bit better. It will also let it heat up and cool down faster. So basically, if you are trying to injection mold and make lots and lots of them, it can make it a much faster, easier process. You've got anti-static. So that is polymers that are good insulators, which can lead to a buildup of statics, which is why dirt and dust tends to stick to plastic products quite easily. So anti-static attracts moisture from the room surrounding to help reduce the static charge. And then you've got plasticizers. So plasticizers make the plastic less hard and brittle at normal temperatures because plastics, take like acrylic for example, if you get a piece of acrylic, hit it on the table, odds are it's going to break. It's a very brittle material. Plasticizers will make that less so. So if you think like garden hoses and those sorts of things, those are not brittle in the slightest. You can wave that around, smack it on the wall, anything like that, and it'll be fine. So those are improving the function. So looking at preventing or encouraging degradation. So we'll look at encouraging first. So you can add biobatch additives that can be added to reduce the degradation time from 100 years to like hundreds of years to a few months. So typically, obviously we know plastic products tend to sit in a landfill, particularly really bad products like toothbrushes that are made out of like 3 different kinds of plastics. So what you want to try and do is encourage that plastic to degrade as fast as possible. So you can get oxydegradable, photodegradable and hydrodegradable. So oxy being it degrades in the air in oxygen, photodegradable meaning that it breaks down with UV light, and hydro being that it breaks down with water. Next you've got biodegradable plasticizers. So similar to plasticizers, and it makes it softer. These make the polymer more flexible, softer and easier to actually physically break down when being recycled anyway. Then you've got how do you prevent degradation? So you've got UV light stabilizers. So this prevents the polymer from breaking down in sunlight. So if you've got plastic products, so I've got a plastic swing and trampoline and things like that in my garden. You may have plastic chairs or whatever in your garden. If you just leave it out there and it didn't have UV stabilizers, over the summers, the colour would fade because it's breaking it down, and it would also become a lot more brittle. So eventually you'd sit on the chair and it would break. UV stabilizers essentially are put into every plastic product that's going to go outside to stop that from happening. You've also got antioxidants, and these help reduce the environmental deterioration of the polymer when exposed to oxygen as opposed to light as well. Now, making the polymers less expensive to produce, so you've got thermal antioxidants. So these prevent the polymer from oxidizing or discoloring due to excessive heat. So excessive heat will happen in the processes, so injection molding and that sort of thing. You're having a huge amount of heat. Same with if it's going to be near a heat source when it's actually used as a physical product, so you want to avoid that. You've got lubricants, so you can add things like wax or calcium. And what that'll do is it'll make it less viscous, when it's molten. So that means basically it's easier to pour, it's less sticky, so you can make more complex shapes at a lower temperature. So you can injection mold really complex shapes a lot easier than you would if you didn't have those in. Then you've got enhancing the aesthetics of it, so you can add pigments. Now pigments are what essentially give it its colour. So tiny particles that you mix into a polymer when it's in molten form, when it's liquid form, that will change the colour of it, almost like food dye or food colouring. So enhancing timber. So natural timbers can have defects such as splits and knots, which can affect the overall stability. Now we have looked at that a little bit in timbers already as well. So this is one of the reasons why manufactured boards like MDF and plywood were developed, as they are consistently the same size and strength, making them very useful for manufacturing, particularly plywood, as well as the fact that you can get them in any shape or size. They're not going to warp or twist or anything like that. So natural timbers do have several disadvantages. You've got strength decreases when they are wet. They are very combustible, so they're very likely to catch fire if they're near extreme heat or open flame. They're incredibly susceptible to fungal insect attack and rot. They are anisotropic. So what anisotropic means is there's different properties in different directions. So I've talked about this a little bit in the timbers theory. That's why plywood is so good. Essentially, because the grain's going in one direction, timber is very strong in one direction, but very weak in the other direction. So we talked about the fact like karate, quote unquote, masters, like breaking boards with their heads and things like that. If that's because they're going with the grain, if you turn it the way around, they like knock themselves out with a plank of wood. So, however, natural timbers are still used in manufacturing because they have very good aesthetic look to it. So, very nice grains, very nice colours, and they are good insulators and a relatively environmentally friendly material because they're not recyclable, but they're sustainable because you can keep growing them. So you can add things like preservatives, so they can be pre-treated. So this will protect it from fungal or insect attack, particularly timber that's going to go outside, so decking, fences, wooden park, like things. I've lost the word there, but like climbing frames, that sort of thing. So preservatives normally use copper as a base because it's a naturally occurring mineral, which has excellent fungal properties. You've got fire retardant properties that can be added to preserve, to pressure treat wood for applications like roof systems, cladding, joists, anywhere where heat may be an issue. You can also treat timber to make it more resistant to wear, like flooring. So the timber will be impregnated with modified natural, oh God, I can never say this word, this cures within the cell structure material and makes it harder. So it's almost like a resin type thing. So simply, you want it to soak into the material itself. It'll cure, so it'll harden. It'll react to the air, and it'll make it much harder. I purposely haven't said that because I'm going to butcher it. If you do this and add pigments, you can take a relatively cheap timber like softwood and use it as flooring, so it'll appear much harder and much denser, much less. It'll do the same job, but for much lower cost. You have, as I said, got pigments. So this will be added to preservatives to give different colours and shades to improve the looks of timbers. Again, more commonly used in outdoor decking and garden projects and that type of thing. So down here as well, I was mentioned BS8417. So this is to do with the treatment of timbers. Now we'll come up. BS stands for British Standards, and then how British Standards work is it's always BS and then 4 digits. Now there are God knows how many British standards, and you'll come across them in loads of different things. But I just wanted to put that in there so you can understand. Treatments of timber come under this British Standards 8417. You don't need to remember that exact number, but understand that British standards and who they are. So manufactured timbers or woods. So these have been engineered to try and remove the weaknesses that we've just talked about. So making sure you don't have those rots, those knots, those twists, and so on. So typically used using sawdust, wood chips, and fibres. So chipboard is made from compressed wood chips with resin. Like urea formaldehyde. This makes it very stable and limits the effective temperature and humidity you can have on it. Because if you have too humid, and it will get soggy and it will literally fall apart because it is just wood chips. It's also uniform in strength because it has no grain, so it's strong, the same strength everywhere that you go. So resins used for manufactured boards can be impregnated with fire-resistant additives, giving it a lot more use for things like internal cladding and flooring because it can withstand the heat a lot more. A lot of manufactured boards also have veneers laminated onto the surface to improve its aesthetics. So, for example, you get things like birch face ply, you can have oak veneered MDF. So it looks like the higher quality material, but half, a third of the price. It makes a big difference. So you do also have something called engineered wood. So these are structural composite timbers and laminated veneer lumber. So they're made from either layering veneer or strands of wood and resin, pressing and heat curing them to produce a stable wooden billet. So a billet would just be like the blank sort of material that you have. This makes them less prone to warping, splitting, or shrinking, making them ideal for like beams and joists because they are incredibly strong. So metal enhancement. So work hardening. So you've got when metal is cold work, so there's no heat applied to it, like bending, rolling, hammering. The crystals within the actual metal structure itself, they're distorted and changed, improving their tensile strength and hardness. So the effects of work hardening can be removed when you annealing the material. So annealing is when you then apply heat to it. So annealing is used to make the work hardening metal like easier to work with by making it less brittle and more ductile. So the metal is heated and then that will slowly cool. So this allows the crystals that you've just distorted to grow and slowly move into place again. Then you've got case hardening. So this is the process of hardening the surface of the steel, not the actual internal part of it, hence the name case, so case going around it. So this is steels that have less than 0.4% carbon. So case hardening produces steel with an outer casing of greater hardness and resistance to surface indentation, while the inside of the metal keeps the softer properties. Generally, this will improve its wear resistance. So essentially, yeah, just putting a protective covering around the metal so it can avoid more wear and tear. So case hardening happens in two steps. So there's carburizing. So this changes the chemical composition of the surface of the material so it can absorb more carbon. So essentially, the steel is put in a ceramic box. Oh my god, I need to check. I need to spell check things, don't I? Steel is put into a ceramic box and packed with loads and loads of carbon. The box is then heated to around 930 to 950 degrees for a set amount of time. This allows the carbon atoms to diffuse into the metal structure. The longer you leave it in the heat, the thicker the layer of carbon will be. Once you've done that, the hot metal is then quenched in water. This cools it very quickly and seals the surface of the casing. So we looked at annealing. So the idea with annealing was that you heat it up and you let it cool slowly, so you don't quench it in water or oil or brine or anything like that. Whereas in case hardening, quenching is the process of trying to cool something quickly. So typically you will either quench in water, you'll quench in oil, or you will quench in brine, depending on how quickly you want to cool it. Then you've got hardening and tempering. So hardening is the process of heating medium and high carbon steels to alter the crystal structure. Hardening, you heat them up and you hold them at this temperature for a given amount of time, and then you quench them, again, either in water, oil, or brine. This increases the hardness properties, but it will also make it more brittle. So basically, it can withstand indentation and scratching, but if you were to apply tough like test to it, it would snap. Once it's done, typically the material is too hard or too brittle to actually do anything with it, so you need to temper it afterwards. So tempering is when the metal is heated to below the critical point for a given time and then slowly air cooled. The exact temperature will determine the amount of hardness removed to it. So essentially what you'll do is heat it up, keep it at that temperature and quench it, and then you'll heat it up again just below critical point and then let it cool slowly again. So critical point is the temperature where the atoms of carbon and steel mix freely before bonding together to become a solid. So you want to heat it up just before that point and then let it cool in. Once you do that, it actually goes to this very nice bluish sort of colour. It's very pretty. So heat it up and then hold it at that temperature, quench it, that makes it hard but brittle, then heat it up again and let it cool slowly without quenching it, and that will remove the brittleness. Okay, so that is the end of enhancing materials. Some questions on the screen for me. Can you please pause the video, answer the questions, and then I'll put the answers on the board. Okay, so answers are there. Again, I won't read through them. Just make sure you've got the right answers written down. If you've got any questions, please let me know and I'll get back to you.